We have looked at series connection of two terminal elements where the same current flows through all the elements and the total voltage across the combination is the sum of voltages. We will now look at parallel connection of two terminal elements, which can be thought of as the counterpart of a series connection with the roles of voltage and current interchanged. Okay. When you have a number of two terminal elements, parallel connection implies that you connect one terminal of all the elements together and another terminal of all the elements also together to a different node, and these two nodes form the terminals of the effective parallel combination. Okay. So, you can put any number of these in parallel. Now, what does this do? You can look at the voltages across these elements. Okay. And if you form a loop here involving the first two elements, you will easily see that V1 equals V2 and these two elements V2 equals V3 and so on. That is because they are connected between the same two terminals. Okay. So, a parallel combination has the property that the voltage across all the elements is exactly the same, and let me call this current I1, this one I2 and this one I3, and clearly you see that the total current, this voltage is V, the total current flowing into the parallel combination is I1 plus I2 plus I3. Okay. So, now you can see that this is the exact counterpart of the series combination. Here the voltage across all the elements is exactly the same and the current of the parallel combination is the sum of individual element currents. Okay. So, with this we can quickly go through all the elements again and see what their parallel combination behaves like. Okay. So, again the reason to do this is, though these are rather elementary, is to gain some confidence that you can reason out everything from first principles. Okay. Let me first look at voltage sources in parallel. So, I have two ideal voltage sources V1 and V2. I connect them in parallel. Now, I form a loop and apply Kirchhoff's voltage law. It tells me that V1 has to be equal to V2. So, what this really means is that this connection is not permitted if V1 and V2 are different from each other. Okay. And if V1 happens to be equal to V2, the whole thing equals a single voltage source of value V1. Okay. So, just like a series connection of current sources is not permitted in general, parallel connection of voltage sources is not permitted in general. Okay. So, it will be permitted only if the two voltage sources are identical, and in that case the result is trivial, the result is also the same voltage source. Okay. Now, one thing I have to caution here is that do not get confused between this and connecting two batteries in parallel. Right. You can always say, hey, I can buy two batteries 1.5 volts and 9 volts and connect them in parallel using two wires. What is stopping me? What do you mean by it's not permitted? Okay. Now, here we are talking about ideal voltage sources, right? If you do have ideal voltage sources, this connection is not permitted. Now, the thing with batteries is that it's an approximate voltage source. It's not an ideal voltage source. It has some resistance in series. So those things can be connected in parallel with each other. What happens is that large current will flow, and then that will reduce the life of the batteries. Okay. But when it comes to ideal voltage sources, connecting them like this will violate Kirchhoff's voltage law and consequently is not permitted. Okay. Now we look at current sources in parallel. So let's say we have these two terminals, and I have a number of current sources, I1, I2, I3 and so on. Okay, all the way to let's say IN. We have n current sources in parallel. So the same voltage appears across all of them, but that's not relevant because the voltage across a current source has no influence on the current through it. And trivial application of Kirchhoff's current law shows that the current flowing here is I1 plus I2 plus I3 all the way to IN. So a parallel connection of current sources is equivalent to a single current source Ix, whose value is the sum of individual current sources. Okay. So this is the counterpart of voltage sources in series. Okay. Now we consider resistors in parallel. So again we have two terminals across which let's say we have a voltage V, and we have a number of resistors R1, R2 all the way to Rn. Okay. Now the current through each of them is given by Ohm's law, and for this particular case it's more convenient to use the conductance form. I will write this current as G1 times V, where G1 is the conductance, this current as G2 times V, and so on, and finally this is Gn times V. And the current here is obviously the sum of all of these, which is G1 plus G2 all the way to Gn times V. Okay. So this is the current. I is some number times the voltage. So you see that this is the same relationship that would exist in a single resistor. Okay. This proportionality would be the conductance of that single resistor. So because of this proportional relationship between I and V, we know that a parallel combination of resistors also behaves exactly like a resistor whose effective conductance is given by G1 plus G2 all the way to Gn. Okay. So if I call these terminals N1 and N2, between N1 and N2 it looks like a resistor, and you can calculate the conductance like this. If you prefer to use the resistance form, the reciprocal of the effective resistance is given by the sum of reciprocals of individual resistances. Okay. This is the form that is probably familiar to all of you, but many times it's easier to use conductance in analysis than resistance. Okay. Now we consider capacitors in parallel. Okay. So we have two terminals across which we have a voltage V, and we have C1, C2 all the way to Cn. Okay, and we can write the expressions for the currents in individual capacitors. We know that the current through capacitor C1 in that direction is C1 time derivative of V. Current through capacitor C2 in that direction is C2 times time derivative of V. I didn't say this explicitly, but I think by now you are used to the idea that when you have parallel connection of capacitors, the voltage across all of them is the same and is equal to V. And finally, the current through this is Cn times time derivative of V. So the total current coming out of here is the sum of all of these things, which is simply the sum of capacitors times the time derivative of V. And again you see that the relationship between the voltage here and the current there looks exactly like that of a capacitor. Okay, that is, if we had some capacitor C effective and a voltage V across it, the current through it would be C effective time derivative of V. And you see that these two are in the same form. So clearly it says that the effective value of capacitance is C1 plus C2 plus C3 and so on. Okay. So a parallel combination of capacitors acts like a single capacitor whose value is the sum of individual capacitors. Now we consider a number of inductors in parallel. L1, L2, Ln, and all of them have the same voltage V across them. And I will mark the currents I1, I2, In. Now we know from previous discussions that the current I1 at a time t equals 1 over L1 integral 0 to t of the voltage across the inductor. Okay, and this is assuming 0 initial condition for the inductor current. Okay, so the total current, which is I1 plus I2 plus In, equals 1 over L1 plus 1 over L2 all the way to 1 by Ln integral of 0 to t V of t dt. Okay, so now we see that this is exactly the same relationship we would have had if we had an inductor whose value equals L effective. Then the voltage and the current would be related by I equals 1 over L effective integral of V over time. So clearly this reciprocal of effective inductance equals the sum of reciprocals of individual inductances. Okay, 1 over L effective equals 1 over L1 plus 1 over L2 plus 1 over Ln. Okay, and this is similar to having resistors in parallel. If you write out the expressions in terms of resistors, we saw that we got a similar form. Okay.